So today is the 6th of March 2026. This is the European final of the IMechE Speak Out for Engineering final, as I said, for Europe. I'm very pleased to announce that we have 4 contestants from Italy, Germany, the Nordic region and Palestine. They will be able to present themselves when they start their presentations. Just a very short introduction to say who you are, so I'd say we could skip that now. I'd like to just say we have judges from different countries in Europe. So I am Daniel Fantoni. I am chair of the European region, volunteer role, nothing special. I'm here to facilitate. I am not a judge. I'm just basically hosting, helping things to go along. Our organizer for SOfE is the young member rep for Europe, who is Prabhu. Prabhu, if you'd just like to say hello to everyone.
Hello everyone, and wish you all the best. I'm based in Paris, and I'm working in the oil and gas industry on the contracting side, and I will be the timekeeper for today.
Thank you. Next, judges, if Andrew, would you like to say?
Yeah, good evening, everyone. I'm Andrew Skinner. I'm the head of engineering for the Great Western Railway, a train operating company in the UK. I'm a former railway division chair at the IMechE and currently a council member.
Thank you. Who's next? Hugo, do you want to say hello?
Hi, hello. I'm Hugo from Portugal. Still afternoon here. I'm a fellow of the IMechE, and I'm a volunteer at the Iberian group of IMechE, as long as at our local engineering association. Well, I run a plant for an international group here in Portugal in the automotive sector. I wish you all good luck, and I'm eager to see your presentations.
Thank you. Thank you. Juliette?
Hello, my name's Juliette Cook. I live in Switzerland, but from the UK originally. I'm a mechanical and a biomedical engineer, so I've always worked with medical devices from R&D, and now I head up global regulatory affairs. So that means making sure that all the R&D, all the production, everything meets all the standards so that we can safely use these things. And I'm so delighted. I'm really looking forward to your presentations. Good luck.
Thank you. And then we have Valentin.
Hello, good evening, everybody. I have participated in this event. I organized this event, so it's very interesting to be on the other side. I wish you all the best of luck. I'm from Russia and the UK, and I'm also now based in Switzerland, like Juliette. And I have healthcare experience. Currently, I'm a data center cooling project manager. So that's a nutshell, and I'm really interested and excited to see what you'll have to present to us. So best of luck.
Excellent. Thanks very much. Okay. Right, so just a couple of points of order, perhaps. Slightly bigger. So contestants will have 15 to 20 minutes for presentation. That is, you must present for at least 15 minutes. You will be warned when the 15 minutes is complete, but keep your own clock going so you know that you must have been talking continuously. You can have breaks, for 15 minutes, and you will be warned 2 minutes before the 20 minutes is complete. At 20 minutes, you must terminate your presentation, and then we will migrate to questions, so questions and answers. The idea in questions and answers is that contestants are asked questions by judges. The judges should ask simple, straightforward questions and not lecture you, so that you have, as contestants, you have time to answer. Be careful with your answers. If you don't know the answer, it is it's legitimate, and you can just say, sorry, I do not know. I would suggest you don't try to answer a question if you don't know the answer. you can think about your answers, be very careful what you say, because that's when you're, it's more difficult in the question and answer than all the presentation put together, I would say. Anyway, and remember, what the judges are looking for is how you present. The content is important, but it's very much how you present, your ability to present, your ability to speak, to be interesting, to capture the audience, to keep an interest level in your presentation. So if you think you've made a mistake, don't worry. It's not so much about the mistakes or the accuracy technically of your presentation. It's about how you present. Very much so. Okay, so with that, I think we can start. I've put up a sequence. It was very arbitrary, let's say. So the sequence is Federica, Oscar, Andrew, and Duha. Does anyone have any problems with times? Because we could change the sequence if anyone has an issue. Because we had said we'd finish by 7 o'clock, but we got the calculation of not very good for engineers, was it? 4 times half an hour was the calculation, but we have to add on time for judges, etc. So if nobody has any problems with the timing, we'll say Federica, if you'd like to.
Okay, can you hear me?
Yes,
Yeah,
I can hear you.
Okay, perfect. I'll share my presentation, just 1 second.
That's fine. Take your time, get it set up.
Okay. Can you see it? Do you see it? Yeah.
I think it's visible.
Okay, perfect. Good afternoon. I'm Federica. I'm a mechatronic engineer.
No, just give Prabhu a second. Prabhu will tell you when he is ready.
Yes, I'm ready. Yeah, you can go ahead.
Good afternoon. I'm Federica, as we said. I am a mechatronics engineering student from Trento, and today I would like to share with you my presentation about time and time measuring, with a particular focus on the evolution of the concept of wristwatches, the one that we probably own. First of all, what is time? Time is the continuous progression of existence, which unfolds itself in an apparent single direction from past to present and eventually to future. If as human have some kind of free will in the spatial dimension, the same cannot be said about time. In fact, we can only move forward and we cannot control it in any way. Despite this limitation, humans have always looked for a way to at least measure time. Let's start from the concept of hour. The idea of hours comes from the Egyptians, and basically they decided to divide the day into 12 hours in a daytime and 12 hours in the nighttime. In a similar period, we are in 2000 before Common Era, Babylonian added the base 60 numerical system, so we have the introduction of minutes and seconds. Later on, Greek scholars redefined those concepts, but we have to wait for the medieval period in Europe to have an actual standardization of all those elements that arose basically when mechanical clocks started to appear. But how can we measure time actually? We see days going by looking at the sun. We can feel the season changing and repeating. And this repetition gives us the concept of years. But when we come to smaller period of time, we do have some kind of limitations. And that's why we need to rely on something that feels time better than we do. This something are oscillating processes. In fact, one of the first mechanisms that was used for the time telling was the oscillation of the mass. This type of mechanism arose probably in monasteries with the purpose of tolling bells and calling monks to attend prayers. As I said, it used the oscillation of a mass, and it was composed by a foliot, which is this horizontal bar. The foliot is moved by a gear train. We have the escape wheel, which gives an impulse to the foliot. it oscillates, and coming back, it disengages from this escapement wheel. The relation between the escapement wheel and the foliot permits to stop and move a train of gears, which will move the displayed hands. The power source is a mainspring, which is coiled inside a barrel and, as I said, works as a power source. The oldest still working example of this type of mechanism is the Salisbury Cathedral clock, and as I said, is still working. This type of mechanism has obviously many limitations. In fact, the foliot mechanism is a non-resonant mechanism, and it lacks of a natural restoring force. It can be tuned thanks to the movement of the masses, but it still has a deviation between 30 to 60 minutes a day with respect to the theoretical time. Around the 17th century, a new type of oscillation was considered for the time-telling purpose, and this oscillation is the pendulum oscillation, which was first denoted by Galileo Galilei. Later on, a Dutch astronomer invented and designed the first pendulum clock, and we achieved a better accuracy and reliability than the previous mass mechanism. This type of mechanism is reliable for small arcs, and it has some kind of limitation, mainly due to the changing of temperature and humidity, but also in the deformation of the material. In fact, the period of this oscillator only depends on the length of the pendulum, which actually changes over time. As time went by, we have improvement of the mass oscillating mechanism with the adding of many other components. This type of mechanism was quite improved over years, and we achieved a state of art around the 18th century. And this mechanism that you can see in the slide is the one still used in mechanical movement of our wristwatch. How does it work? We still have the mainspring, which ensures the power source. The foliot was substituted by an oscillating mass and a hairspring, and we still have the escapement wheel, but it is in an interaction with the pallet fork. Furthermore, we have the introduction of jewels, which, due to their hardness and surface finish, were perfect as bearings in pivoting position. How does this work? Basically, we have the mainspring, which transfers power to a train of gears. The train of gears moves the escapement wheel, and the pallet fork basically gets stuck in the middle of the teeth. By the movement of the escapement wheel and the pallet fork, it is possible to transmit an impulse to the balance wheel. This balance wheel will rotate, and since it is connected to the hairspring, it will be pushed back and will rotate back. This rotation will generate a new impulse, which will be transferred to the pallet fork, which will disengage, and this disengagement permits the motion of one step of the whole train of gear. In fact, the entirety of this mechanism only moves when the lever escapement is free. Here you can see an animation of the mechanism and how the escapement wheel, pallet fork, balance wheel, and hairspring actually interact. These mechanisms obviously have some limitation, mainly due to the interaction of each element one another. It's due to friction, and is also due to technological limitation in the manufacturing. For ages, it was not possible to actually highly improve the precision, and this limitation was only overcame with the invention or the discovery of a new type of oscillation. This new type of oscillation is a piezoelectric oscillation. The piezoelectric mechanism, which was used in the quartz watch mechanism was firstly introduced in the 20s, but only in the 60s we have the mass production of a quartz wristwatch, which was the Astron from Seiko. This inaugurated the quartz crisis, since before we had a more traditional idea, a concept of watchmaking, mainly in the Swiss sector. And later on, we have this Japanese wave of electronic timepieces that were more accurate and at a fraction of cost than the mechanical ones. What is piezoelectricity? Piezoelectricity is the property of a material to deform when a voltage difference is applied, and vice versa. When it is deformed, it will generate a voltage difference. A quartz mechanism is composed by a battery, a quartz crystal, an integrated circuit, and a stepper motor. The quartz crystal is shaped as a tuning fork, and it is grown synthetically in order to obtain a natural frequency of 2⁻15 Hz. Basically, at the beginning of the life of this mechanism, the battery drives the integrated circuit. The integrated circuit applies a voltage difference to this crystal. When the voltage difference goes back to zero, due to the piezoelectric property, the quartz will deform to come back to its original shape, and this deformation will generate a voltage difference. This voltage difference is an alternated voltage at the characteristic frequency of the quartz, which is, as we said, 2⁻15. The integrated circuits amplifies and feeds back this voltage to the quartz. This way we have a self-sustaining vibration, and this vibration is used to obtain the concept of the hertz. In fact, this frequency is extremely high, but inside the circuit we have a component which is a frequency divider, which divides the voltage frequency by 2 15 times. This way we achieve the knowledge of 1 Hz, which is 1 second. Once the 1 Hz frequency is known, the integrated circuit generates a signal which is suitable for the driving of a rotor. This rotor is a Lavette type stepper of a motor. This motor is a Lavette type stepper motor, and basically it is composed by a stator, a single coil, and a rotor, which is a permanent magnet rotor. How does it work? Basically, the integrated circuit sends a current in a shape of a pulse. When the coil has the current, a magnetic field is generated, and the rotor will align accordingly. When the current comes back to zero, the rotor will align with the nearest equilibrium point. This nearest equilibrium point is not the previous one, but is slightly above. And this way, the rotor will always achieve the nearest equilibrium only by moving in a clockwise direction. This rotation is exploited for the motion of the displayed hands through a gear of train. So we achieve the 1 Hz frequency. This frequency is used to generate the signal controlling the Lavette type motor, and this motor is the one which controls the time displaying. The impact of this invention is evident when comparing the complexity of the mechanism. Both of them have a characteristic frequency, one given completely by a mechanical oscillation, the other one is always an oscillation, but the 1 Hz is obtained precisely through the integrated circuit. And as you can see, the deviation from the theoretical time is extremely different. It comes from 5 to 20 per day to 15 per month. But why are mechanical movement that imprecise compared to the quartz movement? An important aspect to point out is the number of elements that we have. In fact, the more the element, the more the errors that will accumulate and translate into the deviation. Furthermore, a quartz movement, since it owns an integrated circuit, can correct some of the error and the deviations. It is also important to point out that for a wrist mechanical movement, the precision needed was industrially achieved in the half of the last century. In fact, here you can see one of the widest spread mechanical movement, which has this code. The colored element are the bearings. And here you can see a sheet of the tolerances that are needed to have a precise wristwatch. And as you can see, we are in the order of the micrometer. The micrometer was achieved in CNC only in the 50s and 70s. This translates in complexity, but also in complexity in the manufacturing, which means major costs. Instead, here we have one of the most spread quartz mechanism. And as you can see, we have 10 times broader tolerances, which means less complexity, which means easier manufacturing and a cheaper time teller. In conclusion, quartz mechanism allow to achieve a great accuracy at affordable prices, but probably the mechanical mechanism will always be an inspiring example of engineering artistry and the seek of perfection that humankind keep running for. And I hope I was clear, and I thank you for your time.
Okay, it's over. The 15 minutes is over. So you completed your presentation, correct,
Okay.
Frederica? Okay, thank you.
Thank you very much. We
Now-
open to questions now. We should have the judges can answer questions. If the judges have finished answering questions, we can open it up to others, but it's up to you now, judges.
May I start? Thank you very much for an interesting presentation. I'm just interested, what inspired you to actually choose this topic?
I extremely love watches, and mechanical watches to me are a good example of a trade-off between poetry and engineering, I think. And it's one of my passions in general.
Mm-hmm. Thank you. So do you have a watch yourself, and is it kind of using the mechanisms you described, or have you got something even more advanced?
Many just to be fulfilled. Yeah, I do have many.
Okay. Do they have the same mechanisms that you described?
Yeah, I have many quartz watches, and as with obviously mechanical watch.
Thank you.
Okay, there is one question from my side. Why do you consider the watches as one of the important innovation, and how it changed the human life, or what is the impact it made on the life?
Well, sure, a social impact, like organization is based on the fact that we all know what an hour is. For example, today we wouldn't organize if we didn't, if we hadn't the same time, for example. And also it's very important in science, I think, because detecting when a second has passed and so on is necessary for experiments and so on. So I think that detecting time in a univocal way is necessary for society, but also for invention, studies, and so on.
Okay. Valentin, would you like to?
Yeah, thank you, Federica. Very interesting. For me, you partially already touched on this, but if you consider the most complicated mechanical watches and the most simple but effective quartz watches, do you think they're similar in some ways? Because they are both at the extremes, but they both provide at the end of the day the function of time keeping.
Yeah, at the end of the day, they both achieve the 1 Hertz frequency in different way. Probably they both have some kind of gears, but at the end of the day, they tell us that existence is going the right direction.
That's interesting. Thank you. Hugo.
Hi, Federica. Thanks for your presentation. It was really interesting. I was listening to you carefully, and I was wondering, do you have any plans to carry on working in this area, or do you have any ideas on future development? Because this technology, actually, it's so embedded in our lifestyle in today's nowadays societies that nobody except those who really like it really look at it deeply. So I was wondering, besides the first question, whether you have any technological developments, any revolutionary vision on this subject, eventually generating a change in society or a lifestyle or an improvement in life of
Okay.
ordinary people around the world.
Well, I think that it's an extremely interesting field, not only for the final product, which is magnificent, but also because it's an exercise of precision. To build the right clock, we need extreme precision. So yeah, maybe nowadays not many people wear watches knowing what they're doing. We generally use phones and so on. But for this sake of precision engineering and so on, they are a great example. I'd love to somewhat have ideas to be part of the change, but unluckily, I still don't.
Hi, Frederica. Thanks so much for that presentation, which I really enjoyed. You've taken us through some steps in technology from the earliest to the present day. Of all those steps, which do you think is the most revolutionary and why?
Steps in general, in the evolution of those.
Yes, each slide presented a step in technology, and I just wondered between which two slides, which step in technology was the most profound for you?
I think it was the introduction of the rotating mass and spring, since it's probably the most studied oscillation still nowadays. Everyone in the engineering study probably studied the mass and spring oscillation, and that really gave the possibility of having a reliable oscillation and so on. So I think that the study made between the 15th century and the 17th century were the most important step of the process.
Thank you.
Perhaps I'll ask a question, if I may, Danica. So how did watch manufacturers manage to change a watch from being a utility technical product into what is now effectively, it's a fashion product, a high value fashion product? It's not just a watch.
Mm-hmm. I didn't get what you said completely.
So how and why did they change just a timekeeping device into a fashion article?
Probably because nowadays fashion, we have time tellers everywhere, from stores to phones to computers and so on. So maybe we do not need a watch nowadays. And since it is, it's actually an accessory. So I think it's due to the fact that we are used to see hours everywhere.
Okay, thank you. Okay. Prabhu, how are we for time? I think perhaps we've
We are 6-7 minutes into it. If there are no other questions,
we're fine then.
we
Okay.
can find them.
Thank you
Thanks.
very much then, Federica. Thank you.
Thank you.
So just whilst judges, if you just start preparing your score sheets for Federica, and Oscar, if you just start preparing to present, and when the judges say they're ready, then you will be able to start. So if Oscar, you just get your slides shown.
Yes, I'll do that. Can you see something?
Black.
Can you see a black screen? Yeah, that's what you
Very
should
black.
see.
Yeah.
Perfect, perfect. That's a start.
Okay, just wait. So judges, do you still need more time, or are you ready? You're all okay? Are you okay, Hugo? Okay, everyone's ready. Okay, so Prabhu, if you're okay, Oscar, you can introduce yourself and start. When Prabhu, just say you're ready.
Yes, I'm ready.
Okay, Oscar.
Okay, welcome, ladies and gentlemen. Just about 2 months ago, I got the pair of beautiful new hearing aids. Maybe if the camera quality is good enough, you can see them. Just in the little body of one of these. Yeah, there it is. Just in the little body of one of these hearing aids are multiple microphones, movement sensors, sound amplifiers, wireless connection modules, and especially important, a microprocessor. Now, this microprocessor interprets all of the incoming signals and decides which frequencies belong to, for example, the cafeteria chef I'm trying to talk to, which come from the shattering plates in the kitchen, and which belong to my friend who yells my name from the rear left. Now, out of all of these sounds, the microprocessor calculates which frequencies to amplify or to suppress to allow me to have a full spatial hearing and a comfortable conversation. And all of that happens in less than 2 milliseconds. Now, this is my real-life use case where I rely on microchips in my daily life. But also every one of you sitting here in front of their screens relies on microchips every day. We all use a laptop or a computer right now. We use smartphones, we use AI, we use, well, at least partly autonomous cars. And even if one of these microchips happens to malfunction and you find yourself getting hit by one of these autonomous cars, you will just get rushed off to hospital to again rely on another set of microchips in, for example, one of these medical robots. So you can see there is really no getting away from microchips these days. And this is why I think that everyone should have at least heard about the way they are structured, how billions of nanoscopic wire connections and transistors allow our modern technology. And once you've heard about that, I can guarantee you that you'll want to know how we are even able to produce these intricate and complex pieces of technology. And after that, we'll take a quick dive into the machine at the heart of this whole production process, the EUV lithography tool. And this is also where I'll be able to share a bit of the hands-on experience I could gain while working at a company called Trumpf. Maybe some of you have heard of them, that produce the lasers powering this machine. Now, zooming into the structure section right here, we can find a standard circuit board. As you know, these circuit boards, they're literally built in everywhere nowadays. Looking at the processing unit right here, we can already see a scheme of one of these microchips. And as you see, it's just a complex maze of little wire connections. Taking a look from the side view, we can see in gray and golden the horizontal connections in X and Y direction, and also vertical pillars called wires that form the electrical connections between our different layers. And as you see, these layers get smaller from top to bottom. Now looking at the foundation layers down there, we can see a third material that's beige colored right there, and this is silicon dioxide. This is just an isolating material that prevents all of our metal connections from touching. And now if we zoom all the way in there down to the bottommost layer, we can find another type of layer, the transistor layer. And transistors, they are basically just switches. You apply a voltage, they switch on or off, allowing us to form a logical 0 and 1. And with that, we are able to perform simple binary calculations, like binary 1 plus 1 equals 1, 0. Now, connecting some of these transistors together allows us to do more complex calculations. And by connecting billions of these transistors together and making billions of calculations every second, a microchip or computer really comes to life. Now, for our modern technology, for autonomous cars or hearing aids, we need to do more and faster calculations. And one of the obvious solutions to doing more and faster calculations is to simply shrink down the transistor size so that we can fit more of these transistors on the same chip. And this has gone so far that in the newest generations of microchips, the smallest feature size goes down to just 10 nanometers. Now, to give you a little size comparison of the dimensions we're talking about here, just imagine you're taking this microchip and scale it up to have the size of the whole city area of Berlin. Then one of the transistors on this microchip would only be as big as a McDonald's cheeseburger. Now, this means two things. First of all, we could fit 14 billion cheeseburgers into Berlin. And second of all, and a bit more important, unfortunately, we're able to fit more than 14 billion transistors on one of the newest microchips. But how are we even able to produce these complex, tiny, teeny, tiny transistors? And the answer is light, but not just some light. Imagine you want to paint a picture. For some part of the picture, you can use a thick marker. For other, more intricate parts of the picture, you will have to use a fine liner. Just in our case, we're not painting a picture using pencils. We are painting the pattern of our wire connections onto our microchip using light. And the thickness of the lines we can paint is not determined by the tip of our pencil, but by the wavelength of the light that we use. The shorter the wavelength, the finer the structures we can paint. Here you can see the light spectrum. Before, in the older generations of microchips, it was enough to use DUV, deep ultraviolet light. But for our new generations of chips, we have to use extreme ultraviolet light, short EUV, with a wavelength of only 13.5 nanometers. That you have a rough understanding of the structure of these microchips and of the EUV light that we use to produce them, we will take a look at how one of these connecting layers is being produced. And it all starts with what's called a wafer. Now this wafer is just a thin plate of pure silicon. Jumping right into the production of one of these connecting layers on top of a few already existing connection layers, we can see that we have the silicon dioxide, this isolating material again. Our plan now is to dig trenches into the silicon dioxide to reach the underlying metal connections, the pillars, and then fill these trenches back up with copper to create the metal connections. And in order to do that, first, we have to apply a layer of photoresist coating. And next up, we can already use the EUV light I introduced before. Now this EUV light is being sent through a stencil that has the pattern of the wire connections we want on our microchip on it, onto this photoresist coating. And with that, we're able to print the fine structures of these wires onto our microchip. And this EUV light is so powerful that it breaks up the atomic structure of this photoresist coating, and we can simply apply a solvent solution to wash the broken down structures away, revealing the silicon dioxide. And all that is left to do is to apply a special etching process to etch the silicon dioxide away. And as you can see, we already reached these metal connections down there. Now we simply have to remove the rest of the photoresist coating, fill the trenches up with copper, and then after we have ground everything down nicely, we are already left with our interim result, which I personally think looks quite beautiful. Now, this process is repeated 40 to 100 iterations, depending on what special kind of microchip you want to produce. And after all of these iterations, we are left with a wafer that is filled with identical microchips. And if we zoom all the way in there, we can find the microchip we have just created. Now, let's take a step back from this production process and take a look at the machine at the heart of it, the EUV lithography tool. Now, this machine powers everything in this production process, and it produces the fine EUV light we need for it. While I was working at the company that produces the lasers for this machine, I learned something new about the incredibly complex interdependencies of all of the parameters and parts in these lasers. And so what is stunning to me personally is that this complexity of these lasers can't even be found in this big machine, this big corpus that is always depicted as the EUV lithography tool, but these crazy complex lasers are actually located in a separate room below this machine. And so when the real complexity starts, the laser beam has long been produced. But to break all of this complexity down a bit, we will take a look at the workings of the laser and this machine through the eyes of a little photon called Jeff. And this is Jeff right there. There he is. Now, Jeff is bouncing around in this laser chamber, this laser cavity, and he's constantly fed with energy in the form of other photons, his brothers and sisters. And they are all trimmed and steered in the right direction to form a synchronized laser pulse. This pulse is called the pre-pulse. It has a power of 5 kilowatts. And after Jeff and his brothers and sisters are being released in the form of this pre-pulse, another pulse is being formed called the main pulse. And these two pulses, they are guided through a set of mirrors from the room with the lasers down there up into the source chamber of our EUV lithography tool. Now, zooming into the source chamber, we can already find Jeff forming the pre-pulse being aimed directly at a tin droplet that was ejected from a tin droplet generator. And just in the middle of this source chamber, the pre-pulse hits this tin droplet, causing it to expand into a plate-like form. And just when this plate reaches its peak size, the main laser pulse comes shooting into the source chamber as well, hitting the tin droplet and instantly causing it to transform into its plasma state. And during the transformation of tin to its plasma state, our precious EUV light is being emitted. And this EUV light is being collected by a massive collector mirror. And this collector mirror, another metaphor, is so even that if you would scale it up to the size of the whole country of Germany, it would only have a thickness deviation of less than 1 millimeter, or 1% of a cheeseburger's thickness. Now, this light is being focused into an intermediate focus. And with that, we reach the third part of our illumination process called the projection optics. First, the EUV light is being guided and shaped by a set of mirrors onto what's called the mask. And this mask is basically just a mirror with a layer of absorbent coating on it that has the pattern of the wire connections we later want to print on our microchip. And so when the EUV light hits this photomask, it is only reflected in the areas we later want to illuminate on the microchip. This EUV light, imprinted with the layout information of our wire connections, is being sent through another set of mirrors, again scaling it down and guiding it down here to the bottom of the machine onto the wafer. And with that, we are already back in our production process. As you maybe remember, the only steps left to do are to wash away the broken down photoresist, dig our trenches using an etching process, and then fill these trenches back up with copper. Now, since progress must continue and humans are never satisfied with the status quo, engineers have been working for decades on improving this technique even further. And if we take a look into the future of EUV, we can find that improving this technique will mainly be possible by tweaking two important factors. First,
Oscar,
yeah.
sorry to intervene. Just the 15 minutes are over. Just to remind you the timing. Yeah.
Perfect. Thank you. Now, we're in the future of the EUV. And as I told you, one of the mechanisms to improve this EUV technique even further and to enable us to print tinier features, we can tweak at the numerical aperture of our optics system. And this numerical aperture, when we tweak it and improve it, we are able to form a tighter focus spot that allows us to create sharper edges and tinier features on our microchip. And the second research field is the process factor. And this process factor incorporates all of the things in this EUV process that influence the quality of our EUV beam. And it can be tweaked or optimized by, for example, simulating the illumination process or optimizing our mask layout. And with that, we have already reached the end of our journey through the world of microchips and EUV lithography. I hope that you learned something new and interesting about the structure, how these intricate wire connections work together to enable us to do faster and more calculations for our modern technology. I hope that you learned something interesting about the production process, how all of these steps work together to allow these teeny tiny transistors. And of course, I hope that you learned something about the crazy EUV lithography machine and Jeff's little beautiful life. So have fun using all of your microchip power devices for the rest of the day, and be aware of possible malfunctions when you see an autonomous car driving by. Thank you.
Thank you. So let's open the floor to the judges to ask their questions first. Judges want to put up your hands, then we can get a sequence. Valentin, please.
Hi, Oscar. Thanks. You clearly have a passion for this field, and it's very easy to see why. It's very interesting. So thanks for the presentation. So being somewhat of a, into computers and components myself, could you tell us what the nanometer fabrication size refers to? Because you said 10 nanometers, smallest feature, but we're now here 5 and 4 and 3 nanometer manufacturing processes. So yeah, could you shine a light on that?
Yeah, that's an interesting question. It's always difficult to keep track of what we are talking about when we talk about the feature size. What I meant was the wall thickness of these transistors. And as you said, there are also 3 and 5 nanometer so-called nodes that are being talked about. But from my understanding, I'm also not an expert, but from my understanding, the node thing that manufacturers always talk about is also more of an advertisement move and name, because we're actually at a point where it is hard to push the boundaries further, because we get quantum and stochastic effects when we have these small dimensions of 5 and 3 nanometers that you talked about. And these are basically the physical limits. So of course there are scientific experiments where there have been smaller feature size demonstrated, but I refer to 10 nanometers.
Mm-hmm. Of course, no, it's understandable. Thank you.
Thank you. Hugo.
Hi, thank you. Hi, Oscar. Thank you for your presentation. Very interesting. Well, I'm just a mechanical engineer, so I don't know much about microchips. But I was listening to you, and I recall that I still remember those days when a computer working at 16 megahertz would be the state of the art, the computer anyone would like to have. Yeah. And as I look backwards, I look into the present, and I see the evolution, of technology, and as well of the means that allow this technology to progress. My question would be, in your opinion, how small can we get into this, so to concentrate as much power as possible per, I would say, per square micron or so, I don't know. And what is the limit on this technology? Where do you see it actually getting exhausted, and with no further room to improve, to progress, and to get more powerful? And what I have in mind when I ask you this is this quantum computing. It appears that.
I'm sorry?
I think we've lost Hugo. So can you I think it's best just to answer the question now, what you've understood.
Yeah, I think I understood your question, Hugo. This is also a bit about what I told Valentin before. There are the physical limits that we are facing right now, with the feature size going down to 8 or 5 nanometers. And these are really physical limits that can't really be pushed any further. So this evolution that has been happening for the past decades, that with the Moore's law, that I don't know the exact law, but that the evolution was very fast, and it's coming to a halt, and it's slowing down because we reached this physical limit. And engineers are now working on, as I said, increasing the numerical aperture. There have also been new EUV tools that have a higher numerical aperture than the EUV machine I just showed you. This is one of the factors they can work on. The other factor that affects the critical diameter or the critical dimension is the wavelength. And as I told you, the wavelength of 13.5 nanometers is the best they can reach so far, because it's already very hard to obtain this short wavelength as you saw. And yeah, the other factor is the process factor, as I told you. This is the third part of the equation that determines how small we can get. And this process factor can be optimized by optimizing the whole process any further. But yeah, I personally think we're slowing down a bit, but I'm really not a total expert.
Thank you. Andrew, would you like to?
Thanks for your presentation, Oscar. I've learned some things there.
Thank you.
Having gone into quite some depth in EUV lithography, do you see other potential applications for this technology?
That is an interesting question. When I had the German final, one of the members of the jury asked me something about the way this technology could be used in, I think it was that it had something to do with space. I'm not sure anymore. I think there are probably other applications, because there is no other way that this EUV light can be produced on Earth. And I guess there are other applications that you can use this special light, but I couldn't tell you one concrete.
Okay, thank you, Oscar.
Thank you.
Juliet?
Yeah, thanks again for an interesting presentation. I'm just curious, if you had twice as much time to do this presentation, what extra information would you'd like to tell us about, and why?
Oh, that's an interesting question. I think I would go further into the limits of this technology, as I already told you. And then I would also go further into the specifics of the EUV lithography machine, because I think it is so amazing. And I would also tell you more about the lasers, because that's what I've been working on in my presentation. I think obviously lasers are very, very cool. But they are just so complex, and there are so many ways and different kinds of lasers that I will tell you about. And then I will probably go on to the optics, because what is so interesting of this optic system is that we are not using normal lenses as you would expect when you want to focus something, but we're using mirrors, because this EUV light has such a short wavelength that it is actually absorbed by all kinds of lenses. And so we have to use these mirrors. And yeah, I would go further into how these mirrors are built up, because they're not like your normal bathroom mirror. They're actually called Bragg reflectors, and they're made out of alternating layers of silicon and molybdenum, and where every layer is only reflecting 3% of the light that hits it. And so this is also one of the factors why we need to gain as much power in the source chamber from the EUV light production process as we can, because with every mirror that the EUV light hits, only 70% in total of the input power are reflected. And so with every mirror, we lose more and more and more of this power. And from start of the EUV light to the finished wafer, to the moment that the EUV light hits the wafer, there's only 1% of the power left. And this is also fascinating, I think. Yeah. So there are many things I would love to talk
Forward to
about.
that next time. Thank you.
Thank you for your question.
Thank you. I think
Okay,
we've
the
come to
10
the end of
minutes
the
are over.
time for
Yeah.
yes. I was going to ask a question, but we can't, so that's fine. That's
Yes.
fine because the judges have asked. So if we let the judges prepare their scoring, and whilst they're doing that, if Andrew, you would like to just prepare
Okay.
your presentation, prepare to present your presentation, and just hang on till the judges indicate they're ready. That's a nice image there.
For you, maybe. I feel like I've been staring at it for too many hours now.
Just give the judges time. If judges want to just put your hand up when you're ready, but take your time.
Oh, we're good to go?
Hang on.
Oh, yeah,
Juliet's
sorry.
okay. Ugo and Andrew, how are you?
I'm good.
So I think everyone's ready. So Prabhu, if you want to tell us when you're ready, Andrew, just you'll be able to start, introduce yourself and do your presentation.
I'm ready. Okay.
Andrew.
So, hello everyone. My name's Andrew Smythe. I'm going to talk to you about giant structural bearings on Storebelt Bridge in Denmark. And my co-presenter is Keep It Simple Stanley, who I need to rein me in as an engineer. I tend to overcomplicate everything. So he's hopefully to tell me to keep it simple. I work for a company called Ramble in Copenhagen. I'm a mechanical engineer in a kind of civil engineer's world, really. So I deal with a lot of structural mechanical devices on bridges and big civil structures. And I'll be talking about bridge bearings today, but these are some of the other aspects I deal with. And other fun stuff like movable bridges as well, dealing with actuators and hydraulics, and a little bit of cathodic protection, if you remember that from chemistry, stopping things rusting. It's interesting, I find, but yeah, not quite as exciting to watch. So the bridge I'm going to be talking about is Storebelt West Bridge in Denmark. So Denmark is a lot of islands strung together by big bridges. Storebelt Bridge is the biggest one in Denmark. It's got 14 million vehicles crossing it every year, about 43,000 trains every year. So it's a really vital link to the rest of Scandinavia from Germany. And here's a picture of it. It's actually two bridges, really. You've got the East Bridge in the far distance. That's the pretty one. It's a suspension bridge. Then there's a little island, and then we have the West Bridge, which is two bridges, really. It is a let's put a laser point on. Yeah, there's a road bridge and a rail bridge. So we're going to kind of zoom down and have a look at that. So why do you need bridge bearings? Well, if you consider that the bridge is actually quite dynamically loaded, it's a 6.5 kilometer bridge, and so over the course of a year between the hot and the cold periods, it actually expands and contracts by about 6 meters difference. So that plus, think about it, there's lots of really strong, heavy winds bashing the bridge deck, heavy trucks going over, trains zooming by, and we hope not, it has happened, but there can be a ship impact as well. So the piers under here, they're very slim and slender, and we need bearings to be there to make sure that the stresses don't go into the piers. So that the pot bearings that are there are basically there to manage the loads and allow the bridge deck to move freely without stressing the piers below. So I'll try and do a quick thing about the bearing layout on a bridge. So this bridge is into 6 sections. So if you focus on one section, we have an actual like fixed point in the middle of the bridge, and then all the expansion and contraction comes away from that fixed point. So the bearings that are furthest away, they actually see the most amount of movement. And we're just going to talk about one pier out of 64 in total. So that's what it looks like. And actually, we have the road bridge to the left, the rail to the right, and there's 2 bearings on both bridges. So yeah, 4 per pier line. And if we actually looked at a photo of one, it's kind of hard to tell what on earth is going on. They're big, they're about 2 meters by 2.5. But we can use SolidWorks to have a kind of cut through and have a look. And actually the reason it's called a pot bearing is this is a pot, and then there is a rubber pad that sits inside. These things take loads of vertical load. They can do 48 meganewtons of vertical load. So this rubber pad, it acts like a liquid. It's designed to allow rotations. And you have lots of seals going around the pad, which are engineered to make sure the pad doesn't like escape. And then we have a top plate on the top here that slides back and forth to allow the movement. And we also have a restraint on the side, and that takes up some of the impact, including from ships as well. So you can kind of tell a bit more when you rip the thing apart, and that sliding motion with the top plate is actually from a polished stainless steel surface under here. And then there's this thing here is a PTFE plate. It's got little dimples in it and bearing grease. It's really well engineered, and you get something like 2% friction coefficient between these two surfaces. So that's one of the most important parts of this bearing design. I'll do an intermission to say there's actually loads of bearing designs. That's why I love working in this field, especially if we're dealing with kind of bridges from the 60s and the 70s. The designers would just kind of come up with any old design, and you'd have to then work out what it's doing. So part of the investigation process we do when we're trying to work out how long a bridge has got to live is to work out what is actually there. And you can see there's a whole different load of variety. Sometimes they fall off the bridges and hopefully don't hit the cars. And sometimes they shear in half. This is one we've got at the moment, and is a bit of an interface with civil engineers. We're trying to work out with this bearing whether the cast aluminium has broken because of a casting failure, or is it due to high rotations, or is it the bridge itself that's not designed well. So yeah, that's a bit of an aside about other things with bridge bearings. It's endless fun. So the project purpose for this one is kind of threefold. We want to know, first of all, how long are the bearings going to last? How can we replace them, or can we replace them? And also, what is the replacement strategy? So that's what we did for the client, which is the bridge owner. So firstly, how long will these bearings last? And the three main things we're looking at is the sliding surface, the corrosion damage that can occur, and also the rubber pad wearing out as well. They're the three main wear factors. How do we do it? Mostly through physical inspection. We've got inspection of data going back to when the bridge opened in 1998. So this is me having a go, and it's a nice sunny day there, but that's not often the case. It only takes a bit of wind, and you can really feel like you've been slapped in the face when you're out to sea like that all day. It's tireless work. I'm trying to measure the PTFE thickness, so using just search blades to like 0.1 degree measurement to try and measure some rates of change. Now, it's not the most accurate, but we've got a lot of data every 3 or 4 years going back right to the start of when the bearings went into service. So we can use all of that data to build up a pattern of how is these things wearing out. And what we can actually see is the fixed bearing that doesn't move much, that hasn't worn down much over time, but the ones that are closest to the ends of the sections where they were moving more, they've worn down, which is, I guess, a bit obvious. We also do a lot of visual inspections. So we're looking at corrosion, the damages to like the most important parts, like the sliding parts, and as much as possible we'll record it numerically so that we have some data that we can then draw on to look at how the damages have changed over time, and then we can work out the rate of change. So physical inspections are irreplaceable, but we can't tell everything from physical inspections. So the rubber pad I mentioned is in there, we can't see it. So one way that we can record what it's doing is take some remote monitoring. So we measure to a 10 Hertz frequency over time. How is this bridge moving? How is the bearing moving? And then we can look at past data to work out how much is the bearing rotated by and what distance has the rotation travel been. And then we can see, okay, the pad is probably at the end of its life. So that's the main ways we can kind of build up a bit of a picture as to how long these bearings have lasted. So we then do a bit of an assessment. So we take into account all the elements that I've mentioned, those key wear factors, and we try and build up a bit of a formula, which was a really hard thing to do. This is what I think I looked like back in the summer of 2023, trying to work it all out. I won't bore you with the formula of how we did it, but essentially what we ended up working out was a lifespan for each one of the bearings. And we could kind of see that within the next 20 years, around about 180 of 290 bearings needed to be replaced within 20 years. And we're looking 20 years in the future because we know this work to replace it is going to be costly and take a lot of time. So that's the kind of the mark we're working to, is 20 years. So everything within 20 years we need to start to replace within this next project. Incidentally, the greatest wear that was found was at the ends of the bridges where the piers are a little bit shorter and it's a bit stiffer, and the bearings are doing a little bit more work, whereas the middle of the bridge, the piers are a little bit longer and they kind of flex a little bit more. So That was the main thing. We found the rail bridge moved a bit more dynamically as well, and it wore down a bit more quickly. So then we moved on to, well, can we replace these? And let's see if we can lift the bridge. To do that, or to get the bearings out, we have to lift the bridge. 48 meganewtons, we can't just pull these bearings out. So we use hydraulic jacks to lift them up. We did a finite element analysis of the structure locally to work out the bridge is really stiff. So we need to lift at the bearings with about a ±2 millimeter accuracy. So we can't just lift up one side and leave the other side down. It would damage the bridge. So we've got to do it really controlled and really accurately. And what we're doing is we're actually using 6 900-ton jacks per bearing to lift up. We're only doing about 4 millimeters lift just to take the compression out of the rubber pad. And we don't need to do any traffic closure or anything like that as well. We do know that the bridge is likely to move over a little bit of time being on the jacks, and we're going to have to realign it a little bit. So we have some lateral jacks as well, which are going to push the bridge a little bit horizontally. And now I'll sort of zoom into a little bit into these hydraulic jack assemblies, because this is kind of fun mechanical stuff. We like to look at this. And these jacks, they kind of act like a temporary bearing, because when we do this work, we're going to be sitting on these jacks for about 2 weeks. The bridge is going to be on jacks for about 2 weeks. So we need to have a kind of a bearing system. And so we've made one. So we have the same kind of sliding materials that you'd have in a bearing, the same kind of lateral restraint as well. And then we've got our jacks that are going to lift up and push it along as well. So I'm just going to show you as a bit of a fun detail that some of the lateral restraint stuff. So when we want to lift the bridge, we first want to kind of restrain it a bit. So we use this little bolt to turn it and clamp it, and we use a retaining screw to stop the bolt moving. And then when we want to push the bridge, we take that little screw away and we use the jacks to really push the bridge sideways. And yeah, so we actually went and did it and made it. We had to use CAD to make sure that we could get all the equipment down onto the bridge. This picture here is taken inside the bridge deck, and then we've got like a little access hatch where it's only like 1.5 meters square. So we had to be really precise in getting all the big equipment down. And it was nice to see this, this model that we made in SolidWorks get actually manufactured and put onto the structure. It just about fitted down the hatch. So that's it all set up, and it needed quite a lot of big equipment, even just to slide everything back and forth. And actually, when you're doing this lift, it's kind of not even that exciting, really. There was some TV cameras for the first of the 3 lifts we did, and I guess they didn't come back because when you're actually doing the work, it's not very dramatic. You end up staring at a laptop screen most of the time, making sure that you're within the limits and the margins. But it was really nice to see it and test the system, and we were really pleased that we were able to lift the bridge and push it as well. So we were really pleased that we were able to test it, and all the systems kind of worked as well. And when we take these bearings out, it's relatively easy because we have these plates that stay in place down here, and all we're doing is unbolting lots of M36 bolts and pulling these 7,000 kilogram bearings out, which will need to get quite a lot of pulling. We have to be really precise about everything that goes back in, because as I said, we're working to 2 millimeters of tolerance between the bearings. So everything we take out and put back in, we need to have like really precise understanding of all the assembly heights and everything. So it really helped to have drawings from the manufacturing of the bearings from the 90s. All the quality control cards that they probably didn't think would ever get looked at, we found were really useful just to see all the measurements of the different plates. So now we have we think an exact picture of what's gone in, and now we know what we can put back in as well. I'll do an intermission again. So it's not always so easy. In this case of store belt, we could just put the hydraulic jacks in, there was space for them, but often with these old bridges, they don't think about that. So sometimes you've got to build towers to put hydraulic jacks in, or some sort of brace off the side of a bridge, so it can get really expensive. So doing the quality, the assessment of the bearings beforehand is really important, because otherwise it can get pretty expensive doing this kind of work. And we've got some interesting lateral restraint designs we need to do as well sometimes to stop the bridge deck falling off. And sometimes you have to smash away concrete as well. This is hydro demolition. We avoided it with store belt, we hope. But it can get very messy if you're using high pressure jets of water to break away concrete. Really expensive and very messy and not very environmentally friendly. So yeah, we always try and avoid that if we can. So then if I go on to the next project we did for the client, which is what is the strategy for replacing these 180 bearings? We want to do it in about 4 years of work. So we kind of worked out the best way is to have 2 platforms running simultaneously, and they probably can only spend about 3 weeks for a pier per time, because we're not working 360 days of the year. We're working to a smaller window, which is based on the weather. So we have to take into account the risks associated with being out to sea. And we came up with some concept designs on how to do that and like how to build a platform. What we sort of come up with is using a crane to lift a platform, which would have to get bespoke made, which would span across both bridges. And then we could also use a transverse crane in between the bridges. Bear in mind, these bearings, they weigh 7,000 kilograms, and we have to take the whole unit off in one go. We can't dismantle it on the platform. So that's quite a big weight that we have to slide around and move off. And we want to get these bearings onto a barge, and then we're going to take them off site. Hello, Andrew. 15 minutes over.
Good stuff. Thank you.
Yeah.
What I will mention actually is that this is out to tender at the moment. So this is only a concept design, and we're expecting the contractors to come up with some quite innovative designs where they're going to have to take into a lot of different things into account. So this is where we'll use the competitiveness of a tender. Going back to the bearings, we're going to upgrade them so we can make the sliding material or the pad material is going to last 5 times longer because of improvements being made to those materials, and the paint is going to be more resilient as well because of the way you apply it. Now, looking at the actual cost of the project, it's about $27 million. The bearing cost is probably about 1/3 of that, which is relatively high. For smaller projects, the bearings cost is relatively small, and the overall works is more expensive. The reason for it is because we've got these massive bearings. They're made of steel, and it's not very energy efficient to make these things. It requires a lot of hot rolling of steel, about 20 tons of CO2 per bearing, which is kind of hard to get your head around. So it works out around about 6,500 UK houses. That's what their energy use would be for a year. That was what it'd be to replace 180 of these bearings, thereabouts, to try and put it into context. So yeah, it's expensive and not good for the environment either. So we looked at, could you reuse the bearings instead? And we think we can. So what would that look like? That would be take the bearing off to a workshop, separate out the main steel parts, and we would shot blast them, clean them up, do lots of NDT tests, and then basically repaint them, machine them down a little bit, and then we'd get the new wearable parts that we've improved, put it all together, and hey presto, we've sort of got like almost like a brand new bearing that most of it is actually being reused. And the effect is that it's about 50% cheaper to do a renovated bearing, which was a little bit of a surprise to us. But when we're talking about very big pieces, there is a big saving. And there's also huge CO2 saving. So it'd be about 1/2 ton of CO2 compared to about 20 tons of CO2 for a new bearing. Now, it's not just as simple as every bearing can be renovated. It might take about 4 to 6 weeks to renovate a bearing. And we can't just have we can't sit around for 4 weeks waiting for the renovation to be done. So when we take a bearing out, we're going to have a brand new one ready to go at the start of the project. So what that means is in the first year of works, we're going to call it an assessment phase. So every bearing that we work on in the first year, we're going to have a brand new one ready to go that we just pop back in. So there's no standing times. But then what we'll do is all the bearings that we've taken off, we're going to refurbish off-site, in the kind of quiet of winter when we have a bit of time. Then we'll assess how the renovation is, and then we will, if they're good enough, we're going to put these bearings back into the second season. And so that way, the rest of the project becomes quite sustainable. So that was a lot of information. Good stuff.
And so we've assessed the bearing lifetime, test lifted the bridge, and planned for the replacement project. And the next stage is going to be appoint a contractor for this year. We go do some detailed design planning, and then we're going to be on site from 2028 to 2032. In terms of the development, we learned a lot from the calculations that we did in terms of the assessment. We'd speak to test houses, and we've improved the way that bearings can be assessed by doing this kind of work. And in the more improvements you can make is there's more modal analysis that can be done to measure damages on bearings and bridges that is kind of being advanced now. So I think I've kind of thrown a few tips that I've came up with along the way, but what I haven't mentioned is a kind of tip for you would be maybe careful now that you know about bearings and driving. Don't look up, because there's a bit of a curse. I find myself constantly looking up at bearings, trying to work out what kind of one it is and what it does. So yeah, be safe and keep your eyes on the road if you find bearings as interesting as I have. And that is the lot. So thank you very much for your time. I look forward to questions.
Thank you very much. Over to the judges for questions. So put your hands up so we can get a sequence. Judges, your questions. Andrew, the winner.
Yes, thanks, Andrew, for that. Captivating, and you've clearly got a real passion for those bearings. My question's around what's led you down this route. It appears that there isn't background information on the life of these bearings, and you're very much having to find that out. Is that because it wasn't known when the bridge was installed, or was it not thought about? And is this question sort of answered for more modern bridges? Is the life of bearings known at the design and installation phase?
It's a question that none of the manufacturers want to answer once they get asked how long will their bearings last, and it's because there's a lot of different environmental conditions. Corrosion comes into it, and then also like the speed of movement of vehicles going over it. One thing that has definitely changed is the materials have got better. So what was used was PTFE. The only kind of standard was for PTFE. Now there's this ultra molecular weight polyethylene that goes about 5 times longer and lasts longer. So also I think not a lot of studies were done into how long these bearings are going to last, but now we're a bit more conscious about it, and there's a lot more data. I think there's more studies, and we have more access to information as well. So we can now predict it a bit easier than they could have done in the past. So they didn't know, to be honest. I think they thought they'd last a bit longer.
Thank you.
Thank you, Juliet.
Yeah, thanks again for another interesting presentation.
Thanks.
If I understood correctly, the first phase was the assessment of the bearings was a kind of project in itself.
Yeah, that's right.
If you and your colleagues had to do that again, what would you do differently based on what you learned during that?
Yeah, I think we would. Well, there was a few things we would have done. I think the first thing would have been we would have worked backwards a bit more. So we would have said, well, we know that we're going to work with we're likely to need to replace 180 bearings. So let's kind of focus on those, and we do our detailed work with that. We ended up spreading ourselves quite thinly because we tried to focus on all of them, and I guess that goes back to kind of keeping things simple. We tried to focus. I think we tried to look at too many damage models and things, whereas if we first worked out these ones are definitely getting worn down first, and we really focus on understanding that. As we did the project, we found more and more people that we'd learned from. So the other thing was reach out to the right people early on and get as much experience as you can.
Thank you. There's a lesson in life that can use all over the place. Yeah. Thanks very much.
So a question from me to follow up. It's a great presentation. I oddly also found myself looking at what looks like bearings or bridges, it turns out. But I want to ask you, is the frequency of the bridge impacted by the replacement bearings? And do you have to assess that as part of your testing?
Yeah, so that's an interesting point. It hasn't been. Usually we learn frequency in terms of the damage to the structure itself, and not so much the bearings. But it will have an effect because the friction coefficient starts to go up when we do it. So we will be taking a modal analysis of the bridge before we do the replacement, and we do one after, and that's become like a more of a standardized thing now on these kind of projects. So with modal analysis, one thing we can really benefit from is AI and data that's out there. So there's now a lot of data about modal analysis on loads of different structures, which we didn't even have 20 years ago. So more and more now we can take like short-term measurements to see what the vibrations are, and then we can work out, comparing to loads of other bridges, what the maybe what the damage mechanisms are.
Okay, great. Thanks.
Cheers.
Ugo? Carry on, Ugo.
Hi.
Your turn.
Hi, Andrew. Great presentation. I was just wondering, how do these bearings react, for instance, to extreme vibrations, horizontal loads from serious earthquakes? Any study made? Any precautionary measures on these? I suppose so.
Yeah.
On these bearings.
Yeah, so these ones, not so much. They design them to like an ultimate limit. So if they go beyond that, then they will replace it. But in terms of vibrations, there's not so much. The rubber pad can takes out some of the vibrations and acts as like a damper. But there are seismic isolation bearings that are used, and I don't have any drawings for these on this presentation, but that becomes like an extra field, and it has its own standards. So when it comes to seismic isolation bearings, there is like a kind of another fork for those, and they look a little bit different, but they're kind of fundamentally the same, the way they work. So pot bearings, no, they don't work so well. They just kind of take out some vibration with the rubber.
Okay. Oh, perhaps I've got a chance to ask a question.
Thanks.
Perhaps you don't want to hear this one. AI, are you starting to look and think about what you could do with AI, given you've got lots of data and lots of difficult situations to understand?
Yeah, it's true. And I think with Juliet's question as well, one of the things would be using AI to have tried to analyze some of it. So particularly around, we had so much data on the corrosion mechanisms inside the bearing, where we'd taken percentages of damages and stuff. And probably with an AI model, we might have been able to work out some better formulas for working out what the damage model was. And then I think also for this modal analysis, that's where it's going. AI models are developing are being able to tell us more and more, like, is a bridge damaged based on its modal frequencies and stuff. And so that's where we'd start to get used as well. So yeah, I think we'd use it for analysis as much as possible. And I'm probably not even, there's probably even more great ideas which I'm not thinking of too. But for sure, there's something there.
There's plenty for the future. Does anyone else have any questions? You don't have to. It's fine then. Okay, well, thank you very much.
Cheers.
Excellent. So judges, if you'd like to start doing your customary scoring. And Duha, would you like to start preparing your presentation, getting it up, getting online?
Can you see my screen?
It's loading. Yes, I can see soft robots. Yep, that's okay.
Just a moment.
Just hang on. We've got a few minutes. Okay. Judges, how are you doing? Two ready? Juliet ready? Just waiting for Olga. So I think Olga's ready. Okay. Prabhu, are you okay? Ready for
Yes.
the
Yes.
timing? Okay. Remember to shout out a bit more when you get to the 15 minutes and minus
Yeah.
2 minutes. Just
Okay.
shout it out.
Yeah.
Okay. Duha, please introduce yourself, and you have 20 minutes.
Hello, everybody. I hope you're all having a great day. My name is Duha Qarain, but if it's easier for you, you can just call me Duha. My topic today is about autonomous damage repair in robots. So machines are progressively growing in importance in our everyday lives. From basic everyday tasks to major scientific missions, it is crucial that we can rely on them. That could be in basic everyday tasks, such as when you're working on your device and you have to make sure that you will be capable to make a meeting or submit a certain assignment that you have, and that could be in major scientific missions all the way in outer space. And so it is very important that we can rely on these machines. But accidents are bound to happen, and much could happen unexpectedly to damage them. And in many of the scenarios that I mentioned, it would be very hard to get to a mechanic in time or at all. That is why it is very intriguing, the concept of robots getting the capability to self-fix without relying on any mechanic. And so firstly, I'm going to start with an introduction of what is autonomous damage repair in robots and some of the subdisciplines that ties into that. Before I dive into some of the most well-researched mechanisms as of right now, I'm going to be talking about self-healing for polymer-based robots, self-repair for metal unit modular machines, and then self-assembly for the case of a high-energy event. Then we're going to talk a bit about the merits and the challenges and evaluate this idea. How far are we from completely autonomous self-fixing systems, and would we want that? Before I finally conclude. What is autonomous damage repair? It is the property of a machine to detect and fix a loss of function without relying on any human intervention. And some of the most well-researched mechanisms as of right now are self-healing, self-repair, self-assembly, and then that, of course, ties into the functionality of built-in redundancy, which I'm going to talk about later. Let's start with self-healing. Self-healing is primarily used on soft robots or polymer-based machines and utilizes chemical reaction. So some of the ways that it is used is through microcapsules, which if we look at the images here, you can see these yellow orbs inside of a soft robot, and these contain a healing agent. Once damage has been dealt to that area of the robot, that healing agent is going to be released, and it's going to harden and fill in the gap that was caused by the damage. This could be done in a slightly better way through a vascular system, much similar to the nerves in our body, which covers more area. It's going to rely on little tubes that break and release that healing agent once damaged. We can also use shape memory materials, which are materials that have the special property of remembering their original form. And so with the appliance of some external stimulus, such as heat, it's going to revert back to the way it looked before. Now that we have an idea of how it is employed, let's look at a real-life application for self-healing, which is in the field of soft robotics. Soft robotics is a subfield of robotics that concerns the design, control, and fabrication of robots composed of compliant materials. Now, because these robots are softer, they are much more useful and safer to use in fields or work where we need the machine and the human to work together. but it is that same compliance that makes it more susceptible to damage. And that is where self-healing would be very beneficial. I'm going to show you now a small video of an experiment done by Cornell Engineering. Can you see the video? Okay. This robot here gets punctured once in the leg and halts for a minute. And that during that time, it's self-healing. After the minute has passed, it continues on its function as usual. This happens for 6 more times in 6 different areas throughout the video. Each time it halts, self-heals, and then resumes its function. Now that was for something as simple as a minor puncture, where the surfaces were still intact, which is what we need for self-healing, for the chemical reaction to take place and for the bonds to reconnect. But what if the surfaces get separated from one another? We're going to talk about 2 scenarios here, and the theory for how they would be fixed, which was proposed by the Tokyo Institute for Technology. In type 1, if the material undergoes material removal, like we can see in the picture above, the surfaces are going to be separated by a major distance. And then there's the scenario of a lengthwise cut, where the material is going to be separated vertically, horizontally. And to fix that, we're going to use pneumatic artificial muscles, which are little muscles or tubes that are within the robot that can contract and expand based on with the application of pressurized air. And so what's going to happen here is in type 1, the muscle would contract and so bring the surfaces back together again, which would then help initiate the self-healing process. And in the second scenario, we're going to rely on a weight shift. So once the tube contracts, there's going to be a weight shift in this part. And so we're going to get some rotational movement, which would then cause the 2 surfaces to collab back together. And so self-healing could take place. Of course, this is all preliminary research, and it faces many problems. One of them is that it's very reliant on certain external stimulus and cannot function as well outside of a lab. So, for example, for the shape memory materials, we need an external stimulus, which is heat, to initiate self-healing. Also, it is limited to 1 occurrence. So, for example, if the microcapsule breaks, that area does not have that healing agent anymore. And so if it breaks again, it's not going to self-heal again in that place. Then it's also difficult to implement on metal since it heavily relies on chemical reactions and bonds. But that is not a big problem because we're going to talk about how a machine comprised of metal can fix itself, which is done through the process of self-repair. Now, self-repair is used on unit modular robots. So we need to have a robot that is comprised of identical modules. And the process, to simplify it, is going to be when the module fails, it has to be detected, its removal has to be effected, and then while that's happening, a replacement has to come in its place, and the parts that it was tied to, failed module, they have to reform around this replacement. And so I'm going to simply explain what's happening in the image here. The yellow robot in picture 1 is the failed module. And within a modular robot, we're going to have subgroups with what is termed master modules and then slave modules. And what's going to happen here is the master of the failed module is going to realize or detect that the failed module has stopped working because it's going to have a loss of infrared signals for 6 seconds. Once it has realized that this failed module is damaged, it's going to start recruiting the replacement while the slaves around that failed module are going to either detach or be the one responsible for its removal. And so the removing substructure is going to pull it out, and while it rotates and ejects it, the master of the failed module is going to recruit its replacement. Now, once the replacement has docked onto the master, it's going to recruit the other parts that were separated from the failed module. And in picture 10, we see a fixed prototype. That is, of course, a mechanism for a static scenario. So the robot would have to halt its function until it is repaired again. Another theory that can be used is having the replacements be a part within the robot's body. So we can use compression and expansion to do that. So in the first image, the red cube is the failed module. And if we look at the upper middle level here, we see that we have 4 smaller robots in the middle. Now, these are compressed robots. What's going to happen is one of them is going to leave its position to replace the failed module, and the robots neighboring it, the modules neighboring it, are going to expand and fill up its place. And it's going to also expand to fill up the place of the failed module. So that's self-repair. And so for self-repair, we're going to have to understand a very important functionality, which is built-in redundancy. There are 2 types of it. Component redundancy, we're going to rely on identical components to replace the failed module, right? An example of that is a system with spare memory cells, where if one of them fails, it can be replaced by an identical component. There's functional redundancy, where it is not an identical component. It can do the same function for a while. For example, in a car, if the car engine fails, the starter motor could replace it for a while. Now we've looked at how soft robots could fix themselves. We've looked at how robots comprised of metal could repair themselves. But what about a more severe scenario where the robot undergoes a high energy event? So the concept here that we're going to rely on is creating the bonds between the modules to be weak enough for structured disassembly. So we want to control the way in which these modules are going to separate from one another and scatter. And to do that, these weak bonds, they're more likely to separate first if we make them weak enough. But of course, they have to be also strong enough to carry out the usual function of the robot. And so as we can see in the picture here, the robot gets kicked, and in the aftermath, the parts get scattered across the room. And what's going to happen here is that the modules are going to communicate with one another through preset patterns or through blinking lights. And once every module has understood its relative position to the rest, they're going to start locomoting using sensors until the parts have docked onto one another again, and we get the fixed robot. Now let's do some evaluation. What do we stand to gain from this idea of indestructible robots? Firstly, for industrial automation, that would mean minimized downtime, and that would ensure a continuous process, more efficiency, and reduced costs. And because robots need constant maintenance, and such a case would create a big loss in revenue for whatever company. And so if the robot could diagnose the problem and fix itself, then that would be very helpful. And then there's the more exciting aspect of home and personal use. Usually, if one of our home appliances gets damaged, we're going to procrastinate fixing them for at least a couple of weeks. And then we're going to have to call in a mechanic, and it's just such a hassle. If the robot could diagnose the problem and fix itself on its own, that would be great help. Then for space exploration, there have been many instances where robots or mission rovers failed to continue their missions because of minor problems that could have been fixed if there was a mechanic on hand. For example, in 2016, the Curiosity rover, it had a simple problem in its drill feed mechanism, and that put the mission on hold for 2 years. There are other examples where that weren't so lucky. The Spirit rover that had its mission terminated simply because its wheel got stuck in the sand. In the medical field, machines are used in surgeries for handling hazardous materials. And so naturally, they have to be reliable in these critical procedures and to have minimized downtime. In terms of environmental considerations, the devices that we use could live for a longer time and fix themselves. That would reduce electronic waste. And similar to the concept of outer space, there are many places where we have environmental monitoring using robots, where there's not a mechanic on hand, for example, in the ocean or in deserts. There are, of course, a few challenges that are posed by this concept, namely material limitations. So functionality is going to be compromised if we're fixating on possible scenarios that might not happen. If we're putting too much thought into how the robot, about possible scenarios where the robot could get damaged, we could deviate from the main functionality of the machine.
Hello, Doha.
Then there's the 15 minutes.
15 minutes over.
And of course, then there's the problem of the complexity of autonomous repair. We're going to need more sophisticated materials, which is, of course, more costly. Then there are a few ethical and safety considerations. I'm sure many of you have watched the movie Terminator 2. You could reinforce that assumption by raise of hands. But in that movie, we have a robot that is basically indestructible, right? It's actively hunting down the protagonists. And no matter what the protagonists do to destroy it, it constantly self-fixes and repairs and regrows its limbs. And while that is an exaggerated fictional scenario, it does pose an important question. How much autonomy are we willing to give to machines? And at what point do they become indestructible and fall out of our control? Now, a problem that is more grounded in reality would be the problem with the labor market. Similar to the rise of AI and the constant and rising worry of AI taking over people's jobs, if the robots did not need maintenance or repair anymore, that would not be, that would put a lot of people out of their jobs, specifically mechanics. So what do we conclude from all of this? There are a few real challenges, both technical, ethical, and regarding safety, that the concept of indestructible robots pose. But we can tell that most of them can be fixed through certain regulations or rules. But if we look at what we stand to gain, there is much that would be automated, and so many of our problems, from the trivial ones up to the major science-related ones, would be fixed. We would no longer be afraid of robots or machines getting damaged when we need them most. And for scientific missions, that would mean continuity of missions and scientific discoveries. And so while we are a far way from completely autonomous self-fixing machines, and all the research so far has been preliminary, it does sound promising for the future. Thank you for listening. These are my references.
Thank you very much. Excellent.
Welcome.
Let's hand over to the judges for question time. Put your hands up. So, Valentin, please.
Yeah, thank you, Duha. Apologies for simplified pronunciation. Amazing topic, a little bit unsettling, to be honest, because especially the Terminator reference, but a very fascinating sector. I think, again, looking in from the outside, I think it's at the very early stages. What do you now see any technology or any sector on the horizon which is probably going to be the first for mass market uptake? You know, like something that will really start the whole trend, like the iPhone started smartphones or something similar?
I'd say that one of the most well-researched ones so far, and the ones that seem closest to commercial use are the ones related to soft robotics, because soft robots are already a trend. They're already being used a lot in factories for soft hands, for the soft grapplers to handle products, and they're much more, the problems that could cause damage to these robots are much more predictable, and any part in the robot getting damaged would just self-heal using the chemical reactions, because the entire body is just comprised of these bonds, and that would allow such a chemical reaction to take place. So I think that is one of the most realistic sectors where these robots could soon start actually self-healing and becoming that reliable.
Okay, thank you.
Thank you. Who's next? Do you have other questions, judges? If not, I'll. Yeah, okay. So, Ugo? Ugo, please.
Idulha, thank you for very much. Very insightful your presentation. I do remember when I was a young undergraduate, a professor telling us about the brave new world of intelligent materials, for instance, self-shaping materials to be used in aircraft wings that change their shape according to the speed of the aircraft, or even smart materials, biologically complying human body and able to be inserted directly into someone's body, yeah, to heal or prosthetic repairs, and I think it's prosthetic. It is said in English as well, when you add things into your body and that need replacement, and avoiding this replacement by new materials. How far are we, in your opinion, to reach that point? You know, what breakthroughs besides robots could you see that could revolutionize one's life, and how far are we from that point? And thanks a lot.
Well, this idea of robots being capable of fixing themselves can be applied to any machine you could think of, including prosthetics. And so if this concept, as it grows, it can be revolutionary for all of these sectors. For example, prosthetics, they're being used. It's very important that you can rely on them because they're related to the medical field. It's very important that the person can rely on that, like one would rely on biological tissue, you know, like an actual arm or an actual leg. So I think that would be very important, because as of right now, prosthetics are very much susceptible to damage. So yes, I think that any sector you could think of, whether it's space or home appliances or devices or anything in relation to the medical field, I think this will be very helpful in all of these fields.
Thank you, Juliette.
Thanks.
You're on mute, Juliette.
That always has to happen, doesn't it, in every presentation?
It does,
Sorry,
it does.
I apologize. Thank you very much for your presentation. So when you were researching this topic, what did you learn from it that surprised you most?
That's interesting. I would say that I was most intrigued by the concept of a robot being capable of fixing itself after a high energy event, because that does sound like the most severe sort of damage that could happen to a robot. And I think I was interested to know that there's work on that and experiments that have been run on it, and that a modular robot could actually rebuild itself after completely breaking.
Yeah, I agree. That was fascinating. Thank you.
Okay, I'll chip in with a question then. So I noticed you started by explaining that self-healing is a bit like a skin repairing or perhaps plant cell repairing. And when you talked about self-repairing of robot blocks, it looks a bit like the way ants collaborate in working. So I was wondering, in this area, are you often inspired by nature, and which areas of nature do you look at for inspirations in how to have self-healing and self-repairing?
Yes, actually, a lot of self-healing, for example, draws inspiration from biology and from nature. Like, for example, for self-healing, there's much research on and the way that scientists are trying to mimic actual biological tissue. There have been also experiments using, for example, frog cells to create, like they use those cells to create material that is capable of acting like actual living tissue. Spiders, for example, have been used as sort of grappler for self-repair, for example. And with the idea of ants, there's an idea of creating mini robots and them creating a sort of hive that is capable of always fixing itself or reforming to a new form if one of the small robots gets damaged. And so a lot of it really draws inspiration from nature and biological tissue.
Fascinating. Are there any other questions from judges or? Okay, thank you very much. That was very,
Thank
very
you for
interesting.
listening.
Okay, so at this stage, thank you, competitors. I think that's excellent. Judges, just finish your scoring for Doha. The judges, we will move into, so contestants, please stay in this meeting room. Judges, we will move into another room for 5 or 10 minutes. We will do a scoring, and then we will come back in about 10 minutes and tell you. Excellent. Well, that was really good. So how do I summarize it? I think the judges, so we added up the scoring. We looked at the results. We had a thought if it made sense. And we have come up with the winner's name and the runners-up name. The judges were all unanimous in saying, well, it was very difficult because really all the contestants were good. And that's true because you were all winners in your own group or country heats. I think we all, as judges, and myself as the mediator and Prabhu as the, say, organizer, are really pleased because the objective of the SOfE competition is to encourage the improvement and the speaking and presentation abilities of engineers. And we see how this, over the years, we see how it is improving. You're all learning and doing much better than years ago. I think it's a bit unfair also that these are remote presentations. When the competition started, and the competition's been going for many years now, I've forgotten the number, it's on like 20 or 30 years. It started off as face-to-face presentations in the United Kingdom, so in front of people, and we try to have as many SOfE competitions face-to-face as possible. In the international area, we tend to find it's obviously more difficult than the IMechE people in the UK. So we've all learned how to do presentations remotely a lot, and in particular since COVID, everyone in the world is now doing lots more remotely. And it's nice to see different tools are being used. It's not just PowerPoint presentations. There's a variety of different tools that are being used. And it's nice to see how young engineers are very much more confident in speaking and are able to give very much clearer explanations to people. And remember, in this competition, we're trying to encourage presentations to non-technical people. I think here it just so happened that everyone that's judging is an engineer. In some cases, we managed to have non-engineer or non-technical judges. But I think it's very good. One thing I would suggest, I think the most difficult part is question and answer. And it did come out in a couple of cases that everyone hesitates. I'm hesitating now. When you have questions and answers, you don't always know the answer. You can be a bit more honest, and you can just say, sorry, I'm not really sure how to answer that, or something like that, carefully. It's better than trying to find an answer that doesn't necessarily make sense. Or if you don't understand the question, and some of the questions we waffled on a bit too much, sometimes the judges said a bit more than a question and the question itself got a bit lost. So that was a good test of how you handle it. So don't be too shy in saying, sorry, what was the question? Or the technique is you reply by saying, I have understood that you're asking me, and that gives you a few seconds to think about how you can reply. And some of you did that. So very well done anyway. Before I announce the runner-up and the winner, did any judges have any other comments that I forgot that we said we would mention?
Can I say something that we didn't discuss, but I would love to mention?
You can do, certainly.
Thank you very much. It was fantastic. We may all be engineers, but the range of topics there was so diverse and so clearly explained. I've left feeling like an expert. And the only other bit of feedback I'd give actually is all my presentations are online now. I'm home-based. Everything is in this little screen, just about. So it was great that you did that, because it is real life for lots of us. The only tip I'd give is, yeah, make sure that you kind of get rid of your backgrounds, and all of you are pretty neat actually, and get good lighting. And if you have to do this again, you've all got clear sound and microphones and things. So yeah, you've adapted really well. Thank you.
Yes. Oh, one other tip. Always try to have a backup, because things do go wrong. I run so many of these different meetings. Critical ones, I always have two PCs, or maybe also an iPhone and an iPad, as many backup solutions as possible, because things do go wrong. It's inevitable. Usually it's the most important presentation you do is the one that goes wrong. Okay, so we do have a run-up and a winner. Prizes, I can't remember exactly the prizes. Prabhu, do you remember? I know certainly the winner is invited to the global IMechE SOfE final for 2025. Remember, this is the 2025 running into 2026, and that will be in Istanbul in 2 months' time. It's in Istanbul. It's the second year running we're trying to do this. Last year we had our meeting for the ISB IYMC, so that's it, the International Strategic Board and the International Young Members Committee meeting, and we had the SOfE Global Final planned in Istanbul in April last year. I got to Istanbul a couple of days early, and there was an earthquake. The whole thing was cancelled, and so I had to go home, and other people were told not to arrive because there was a bit of worry. So we're having a second attempt this year, and let's hope nothing else happens. I mean, there's a bit of a concern at the moment for arrivals because flight routes are a bit disrupted, but we still have two months. Hopefully that will not happen. Am I doing what they do in competitions? Just keep the tension going before announcing. That's what I'm trying to do. Okay, so the runner-up, microchips and EUV lithography, Oscar Barthel. So congratulations. Thank you, Oscar, for doing that. And sorry you didn't win, but anyway, yes. We don't say who the third and fourth are. We just concentrate on the run-up. And the winner is Giant Structural Bearings on Storebælt Bridge, Denmark, Andrew Smith.
Great. Thank you very much.
Congratulations.
Thank you.
So, Andrew, you've created a problem for me because you're supposed to have been the
Yeah,
helping me.
I have to work on
Never
that.
mind. That's another question.
Yeah.
So thank you very much. Congratulations. What happens next? I was supposed to be sharing this. I can share now the screen, so you can see it written. Be coming up. You should just about see that there. So that's. Can you see it? The official version, hopefully. Okay. There's a form that we fill in. If we're short of data, we'll check with you. We fill it in there. There's a prize, a monetary prize for the winner. I can't remember. Prabhu, is there a prize for the runner-up as well? I'm not sure.
Yes, there is a one, Daniel.
Very good. Okay, and everyone will get a certificate as well. So thank you very much. We will get in touch with you with the follow-ups. If any of you competitors would like to ask for feedback from your presentations, that's also possible. If you can write to me if you have particular questions, and I will either try to reply myself, or I will share it with the judges, the other judges, and maybe they could give you some feedback if you like. But to be honest, you all did very well, and obviously you've been practicing well, and you seem to be on track. So thank you all very much, and it's been a very, very pleasant. Well, it's more than 2 hours now. So back to your evenings. Goodbye to everyone. Thank you very much.
Well done,
Well done,
everyone.
everybody.
Thank you for organising. Thanks to the judges and everyone watching.
Congrats.
Thank you. Congratulations.
Thanks, everybody. Bye.
Good evening.
Bye.
Ciao.
Bye.
Bye.
Good evening.